Hello, this is lecture number 5 on transfer function. Especially in this lecture, we will find the transfer function of electromechanical systems. We have seen in the previous lectures a pure mechanical, pure electrical, hydraulic system, but this very special lecture, it is based on the electromechanical systems. Now, we will see this electromechanical systems. Electromechanical systems. Especially there are two standard systems. Many systems are there, but the standard two systems, the one is called armature controlled DC servo motor, and here the field controlled DC servo motor. Servo means what? Closed loop control system. There is a feedback servo. Okay, and it is the closed loop control system. There are two types: armature controlled DC servo motor and field controlled DC servo motor. Let us will see. We find the transfer function of, first is called armature controlled DC servo motor. Question is like this: find the transfer function of DC controlled, or otherwise we call armature controlled DC servo motor. This is electromechanical. Why it is called electromechanical? Because the input is electrical, the output is mechanical. What is the mechanical? Rotation of the shaft. What is the electrical input? Voltage. Now first we have to draw a figure, that is resistor, inductor, then here this is a motor, and a resistance RA, LA, then PA, then IA of T, armature current, armature voltage, armature resistor, armature inductor, and motor, and the output of the motor is a shaft. There is a disc. Okay, so the inertia, mass moment of inertia of the disc is J, and torsional damping CT. So here the motor has IF, field current is equal to constant. We know that J equal to mass moment of inertia, kg meter square. Mass moment of inertia. Disc, half mr square. If you take a disc, half mr square. And CT is called torsional damping coefficient. There is a oil, inside there is a piston and cylinder oil, it is rotating, torsional damping coefficient. The unit is Newton meter per radian per second. It is a function of velocity. When the velocity increases, the opposition is increases. J and CT are opposition. The output of the motor is torque as well as the angular displacement. Final is both two outputs. The final output is theta of T. Okay. And here the T is what? Torque developed by motor. That is Newton meter. And theta of T is called angular displacement of shaft, that is in radians. Okay. So here one more thing, here there is a back EMF or voltage across the motor. The voltage across motor is called back EMF. Voltage back EMF electromotive force or voltage across motor. Voltage across motor. Okay, so this is the input. PAI of t is input. The output is theta of t. What we supposed to find? Theta of s, Laplace of output. VAI of s, Laplace of input. That is called transfer function. 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 Now, what we have to do? Here there are 4 equations. The hint I will give, there are 4 equations. The one is a pure electrical equation. Second are 2 electromechanical equations, and one is pure mechanical equation. There are 4 equations. 4 equations. The first is called electrical. Second one is called second and third is called electromechanical. And third is also called electromechanical. The fourth one is called pure mechanical. There are 4 equations. We have to write 4 equations. First I will consider this circuit. I will draw a electrical, then 2 electromechanical, and the fourth one is called mechanical. Okay. Now I will write the first pure electrical system. I will write the equation for pure electrical system. By considering this electrical network, the input voltage is equal to voltage across resistor plus voltage across inductor plus voltage across motor. That is back EMF. By considering the pure electrical one. So, applying Kirchhoff's second law, voltage law, the input voltage is equal to voltage across resistor plus voltage across inductor plus voltage across motor, voltage back EMF, voltage across motor. Say this is equation number 1, pure electrical. Now, I will write the electromechanical. The back EMF is nothing but, when the back EMF goes on increasing, what happens? The velocity of the shaft is increases. The directly proportional velocity is d theta by dt. So EB of t equal to kb d theta by dt. What is kb? kb is called motor constant. kb is called motor constant. This is equation number 2. This is called electromechanical equation second, because input is electrical, output is mechanical. Velocity d theta by dt. Now you have to put equation 2 in 1. I will put equation 2 in 1. 2 in 1. What I will get? You have to see here. PA of t equal to RA of t plus L di of t plus kb d theta by dt. So now I'll convert differential equation into simple algebraic equation by using Laplace transformation. You know that the Laplace transformation d by dt is s, and d square by dt square is equal to s square, and here t equal to s. So applying the Laplace transformation, V of s equal to R IA of S plus L d by dt is S, and I of t equal to I of S plus KB S d by dt and theta of S. So I will take I of S is common, RA plus LAS plus KBS theta of S, VAI of S. This is equation number A, or equation number A. Here, okay, I want theta of S, but I don't want intermediate current. I have to remove this intermediate current. Now, total 4 equations I required. Already I have written 2. One is electrical, one more is electromechanical, and remaining are electromechanical is 1 and mechanical is 1. So I'll write one more electromechanical. I'll write one more electromechanical. What is the one more electromechanical? So how the torque? I want to increase the torque. What I supposed to do? The current directly proportional to armature current. When the armature current increases, the torque increases. This is constant. Field current is constant. So I'll write the torque is directly proportional to armature current. So T of T is equal to KT IA of T. What is the KT? Shaft constant. KT is equal to shaft constant. This is equation number 3. This is equation number 3. But I don't want T of T is also intermediate variable, but I want theta of S. So finally one more. This is a electromechanical equation. Okay. So now remaining is pure mechanical equation. Pure mechanical equation. So I'll write once again. P of T equal to KT I of T, and this is equation number 3, where KT is equal to shaft constant. Next, the fourth one, pure mechanical one. How to write a pure mechanical equation? Suppose this is a shaft. You know that for the applying torque, the torque developed by the motor immediately, inertia torque J or I, and one more is called due to the oil, due to the damping, the torsional damping coefficient CT, now damping torque. This is also Newton meter damping torque. Inertia torque is also Newton meter, and the torque developed by the motor is also Newton meter. Now applying D'Alembert's principle for equilibrium, so now I'll write clockwise are positive, and anti-clockwise are negative. So now T of T equal to J theta double dot plus CT theta dot. This is equation number 4, because I want to remove the T of T term. Now I'll equating 3 and 4. I'll equate 3 and 4. I'll equate 3 and 4. 3 and 4. I'll get KT IA of T is equal to J theta double dot T plus CT theta dot T. I'll write in the differential form KT IA of T plus J d square theta by dt square plus CT theta dt. Now what I'll do, I'll take the Laplace transformation. I'll take the Laplace transformation. After that I'll substitute IA of whatever IA of S, I'll substitute here. So now taking Laplace transformation, KT IA of S, J, you know that d square by dt square is equal to S square, d square by dt square is equal to S square, theta of S plus CT t by dt is s, and theta of t becomes theta of s. So now Ia of s is equal to theta of s js square plus cts divided by kt. Equation number B. This is called equation number B. Equation number B. Now you have to substitute finally the equation number B in A. B in A. B in A. If you substitute the equation B in A, you will get the final transfer function. You will get the final transfer function. Okay. Now I will substitute equation number B in A. Pi of s is equal to theta of s js square plus cts divided by kt into Ra plus Las plus Kb plus Kbs theta of s. Now you take theta of s is common. You take theta of s is common. Js square plus cts Ra plus Las Kt Kb s divided by Kt. So now theta of s divided by Pa of s, Laplace of output divided by Laplace of input, that is called transfer function, that is equal to Kt divided by Js square plus Cts into bracket Ra plus Las plus Kt Kb s. This is the final transfer function. This is what? Final transfer function. Now you see, this is the final transfer function, Kt divided by Js square. How to remember this? You see here, Js square plus Cts. Js square is the resistance, inertia, Js square of this plus Cts, because it is a function of velocity. Yes, S square means it is a function of acceleration. So inertia of this plus inertia of this, opposition of this plus opposition of this, Js square plus Cts, bracket complete. Then a resistance of inductor Las plus Ra, the resistance of electrical, resistance of mechanical multiplied by resistance of electrical, plus motor constant and Kb Kt s, and in the numerator is Kt. This is the way to remember. Very easy to remember. Js square plus Cts, bracket complete, Las plus Ra, bracket complete, plus Kt Kb below and Kt Kbs below, and above is a Kt. It's very easy to remember. So now one more electromechanical system, that is called what? Armature field control DC servo motor. So one more important, the transfer function is field control. These two are the, in any book, these are the very standard systems to electromechanical systems. Input is electrical, output is mechanical. In this case there are 4 equations. One is pure electrical, 2 are electromechanical, 1 is pure mechanical. So total 4 equations. Okay, I hope you understand this derivation. Next lecture we will see the armature controlled DC servo motor. Thank you.